All right, welcome back to another episode of Science with Surbat. Today what we're going to be talking about is unstable nuclei and radioactive decay. Before we get going into the details of these notes, there's a couple of objectives I would like you to be able to accomplish by the end of this video. So objective number 1, explain the relationship between unstable nuclei and radioactive decay. And objective number 2, characterize alpha, beta, and gamma radiation in terms of mass and charge. So let's remember where we've gotten to in this chapter. We started out with the history of what the atom was. We then established the subatomic particles, the protons, neutrons, and electrons of an atom. And the last section, we took a look at the specific calculations that can be used to find the mass number, which consists of the number of protons and neutrons of each and every atom's nucleus, that center. And we also took a look at neutral atoms, and we said that neutral atoms have the same number of protons and electrons. Now we need to go one step further and figure out, well, what happens if we change around parts or pieces in the center, in the nucleus of the atom? Well, when we do that, when we adjust what parts or pieces are in the nucleus of the atom, we get radioactivity. Okay? So, what we want to look at is this, and this is a chemical reactions review. All right? You've probably seen chemical reactions, you've probably dealt with them in the past, but with a chemical reaction, we have a change of substances, and this occurs because atoms are rearranged. However, we see here a very, very important word. The identities of the atoms do not change. We'll learn later on that this process here, the chemical reactions, or what happens during a chemical reaction, is just the exchange of electrons. You can see that on our left-hand side of the equation, we have the same atoms, or we have the same elemental symbols listed on the left as we do on the right. The only difference here is Mg for magnesium and copper have now switched places. Okay? So again, we did not adjust the atoms that we are dealing with. In nuclear chemistry, we are going to adjust those atoms, okay? So this right here is going to be different from what we're going to explain in these notes. So let's get right to it and let's talk into nuclear reactions. So nuclear reactions are defined as reactions which involve a change in an atom's nucleus. So now we're going to affect the number of protons or neutrons, or a combination of both, in the nucleus of the atom. As a result, what happens is we change the atom that we are working with. Remember, change in number of protons means we change the atom that we're working with. All right, so just a few terms to be familiar with. Radioactivity is when we have a substance emit radiation. Radiation is these rays or particles of energy that are emitted, in this case, for us, we're going to say out of the atom's nucleus. Again, nuclear reaction, we are changing atoms because we are affecting the number of protons and electrons, or excuse me, protons and neutrons in the nucleus. All right, so we move on here to radioactive decay in more detail. So what happens here is this. We have unstable nuclei. And what we mean by unstable nuclei is all of a sudden we have way too many neutrons to protons. We've thrown off this ratio in our nucleus, and something has to give. And that something that gives is energy, or particles, or rays that we define as that radioactivity. Again, nuclei are unstable because they have non-even or uneven parts of our neutrons to protons in that nucleus. Now, what happens is that a nucleus or an atom is going to want to be stable. So they're going to break down and break down and break down until they find that relative stable form. And that's what we're looking for. That's why atoms emit that radiation. They're trying to give off that energy to get down to a stable atom. They want a stable proton to neutron ratio. All right, so let's go ahead. Let's jump right into the specific radiation that we are dealing with in this class. So we start out with alpha radiation. And alpha radiation is radiation that is deflected toward a negatively charged plate. Okay, great. What that really means is alpha radiation is positively charged. So alpha radiation specifically is going to contain 2 protons and 2 neutrons. So it's going to have a thing or an item that has a positive 2 charge and a mass number of 4. Okay? Now, for us, very important to reference this symbol right here. Alpha radiation can be represented by 2 ways. Way number 1, which we will most often do in this class, is by writing the helium nucleus, and we have the atomic mass of 4 for a helium-4, and then the number of protons, which is 2. And then we can also write it using that Greek symbol alpha in that place here. Now, we are going to go through the example of the alpha decay of radium-226. However, I want to show that to you on the next slide. So, for the example, all I need you to do is say, see next slide. All right, so let's transition and let's actually go through that example by writing out our nuclear equation. So a nuclear equation is just defined as a type of equation that shows the atomic number and mass number of the particles involved. So what we're really going to do is we are just going to do simple addition and subtraction to understand what does the atom decay to. So if you have not already done so, it might be helpful to grab a periodic table. And before I bring mine into the center here, I want to emphasize this. We have this underlined word of conserved. And what we mean is that mass and the atomic number is conserved. For us, that means we're going to account for equal parts on our left and right hand side of our nuclear equation. So let's get to it. We want to show the alpha decay of radium-226. So the first thing that we are going to do is we are going to find the symbol for radium. Okay, so you find your periodic table and we look real closely. Radium has the symbol Ra. Now keep a close eye on that, but I'm going to write the symbol Ra. All right, so now we need to write in the upper left-hand corner the mass number. For us, this is really easy because the mass number is shown here in our isotope notation right after we've written that word radium. So we're going to write 226. And that's going to become our mass for radium, radium-226. Now in the bottom right-hand corner, what we're going to write is the atomic number, which is equal to the number of protons and is that whole number found in our elemental box for radium, and that is 88. So we're going to go ahead and we are going to write down 88. Now, what happens here is that it decays. So an alpha particle is going to be emitted. Decay means emit. So what we can do, if it says decay, we can go ahead and write that particle. Now, if we have, or we take a look at this chart down here, we can see that the symbol for alpha radiation looks exactly like this. An atomic mass of 4 an atomic number of 2, and we write that He, just like we saw on the previous page. Now, what we do here is we need to figure out, well, what did radium decay to? So, what we're going to do first, we're going to ask ourselves, okay, 4 plus what? Or 4 plus X equals 226. Again, what I'm saying is 4 plus a number equals 226. The answer to that is 222. So the new mass number of the element that is being decayed to, or that radium decayed to, has a mass number of 222. We do the same exact idea for the atomic number. So we have atomic number of 2. 2 plus a number equals 88. Well, 2 plus 86 equals our new atomic number. This is very helpful because we turn to the periodic table and we say, okay, the element with the atomic number 86 is shown here as Rn, and that stands for radon. And so what we would do here is we would write Rn, and now we have completed our nuclear equation. I want to point out two things. Again, we've conserved mass. 4 plus 222 is 226, which is the same mass number on our left and right hand side. 88 is on our left hand side for our atomic number, and if we add these two numbers together, 2 plus 86, that equals 88. All right, so let's do the same thing for two more pieces of radiation that we are going to learn in this class. The first type is beta radiation. It said here it's deflected toward a positively charged plate. That means it's negative. It also has a -1 charge and can be represented by the Greek symbol of beta, and it has a mass of 0 but a charge of -1. So the best way to see this is go through another example. So our example is this. We have carbon 14. So the first thing that we do is we look up carbon, we find its symbol, it's C, and we start out by putting the mass number, which is seen here, carbon 14, in that upper left-hand quadrant of our C for carbon. And we turn back to the periodic table to find our atomic number of carbon, which here is listed as 6. So 6 is our atomic number. We then go through a beta decay. So that means it's emitting that radiation on the right-hand side. So we'll draw that arrow. We put the beta symbol. It's a B with a tail. And then we put these exact numbers, 0 and -1 on the lower left. We then add together 0 plus a number equals 14. Well, that's pretty easy. 0 plus 14 is 14. Then we say to ourselves, -1 plus some number over here equals 6. Now be careful, this is a -1. So we have 7. 7 plus a -1 equals 6. So what we do, we look for the atomic number of 7 in our chart. We find the atomic number 7. It's located right here on the periodic table, and it's the symbol N for nitrogen. So carbon 14 going through beta decay has decayed to nitrogen 14. Now I want to point out one more thing. 14 plus 0 is equal to 14. So on both sides of the equation, 14 is our mass number, and we have shown that we conserve mass. Then we notice here 7 plus a -1 is 6, which is equal to the atomic number or number of protons on our left-hand side. So again, I emphasize our atomic mass and our number of protons should be equal on the left and right-hand side of the equation. All right, one more type of radiation that I want to talk about, and then we will be finished with Section 4 notes. This type of radiation, you probably heard of it before. It's what makes the Hulk the Hulk. We have gamma radiation. So gamma radiation is not deflected towards a positive or negative charge. That means it has no charge or is neutral and has no mass. So it has no charge, no mass, and usually results in the formation of a new atom. So what this means is you're going to have energy that is emitted but doesn't affect the number of protons or the atomic mass of a particular atom. And it's seen here by the Greek symbol gamma, and you see here it has an atomic mass of 0, and the number of protons is also 0. And usually it accompanies beta or alpha radiation. So let's go through this. I combine a large portion of what we have learned. So we have uranium-238. It goes through alpha decay, and also gamma rays accompany this alpha decay. So we start out here with uranium, and we want to find the symbol. The symbol on the periodic table is U, so we look for U. We, in the upper left-hand corner, write down 238 because that's the mass number, so we write down 238. And then in the lower left-hand corner, what we do is we write down the atomic number, the whole number here with uranium, which is seen at 92. Now, it says, the problem says that this uranium goes through alpha decay, which, remember, if you look back in your chart, is listed exactly as such. 4-2 with that symbol helium or a helium nucleus. And we need to also write down gamma rays. Now, gamma rays are shown by this symbol, and so we have almost like an upside down Y. The nice thing about gamma rays is they're not going to affect our number of protons or our mass number. We then need to add up our left-hand side to find out what what atomic mass needs to be on this side. So I ask you this: 4 plus 0 plus some number equals 238. Again, 4 plus 0 plus some number up top here equals 238. Well, we get 234. Okay? Now we do the same thing with the bottom. So 2 plus 0 plus some number equals 92. Well, that number there is 90. Okay? So what we do, what's really important for us, is that we look up the element with the atomic number of 90. So on our periodic table, we look for an atomic number of 90. We find it right here. It has the symbol TH for thallium, or excuse me, thorium. Thorium is the symbol and name associated with the atomic number of 90. So we have TH. All right, so that's how we would show our types of radiation. Now, I want to emphasize this one more time, and that is this: the atomic mass must equal each other on the left and right hand side of the equation. So that means if there's multiple things we must add, and the number of protons or atomic number, these bottom numbers, must add up to equal each other on the left and right hand side. Hope you have enjoyed this particular episode, and as always, make sure you subscribe.